So welcome students. Till now in this particular topic we had a discussion over resistor, combination of resistors, cells, combination of cells, many things you have come across, and even you have worked out few problems also. What you notice in all this discussion is you have discussed all these things using a one fundamental law called Ohm's law. It may be your series or parallel combination of a resistor, it may be a series or parallel combination of a cells, or it may be the problem solving till now in the topic. Whatever you have worked out, it is simple circuits. Whatever the problems you have worked out is a simple circuit. Those simple circuit can be simplified using a very simple law called Ohm's law. But when the circuit becomes slightly complicated, such circuit cannot be simplified only using Ohm's law. In such cases, you need to take a help of one more set of laws given by a person called Kirchhoff. So actually it is pronounced as a Kirchhoff, but doesn't matter if you pronounce as Kirchhoff. So you can call it as a Kirchhoff's laws. This is the topic of discussion. Before you take up a discussion over Kirchhoff's laws, you should know about some of the technical terms which we frequently use in the topic. One is, there is something called node. This is one of the technical words we use. Node, which is also called as a junction. Node or a junction. And one more technical term which we frequently use in our discussion is mesh or loop. We'll begin with what do you mean by node or a junction. For that, let me take up a very simple circuit which you are already familiar. It is a parallel combination of resistors. Let us say I'm having two resistors R1 and R2 connected in parallel. At this stage you know what do you mean by parallel combination, and this parallel combination is connected to a cell. Cell is having some EMF E and internal resistance small r. Obviously this is an electrical network, or in a simple word, electrical circuit. Here this particular point I can call it as node or a junction. For your reference, I will name that point as A. A can be called as a node or a junction. Even this particular point which I have named as B can be called as a node or a junction. Question is, what do you mean by node or a junction? Node or a junction is a point in an electrical network where more than two conductors meet. Node or a junction is a point in an electrical network where more than two conductors meet. See, for example, here, can you please tell me how many conductors are meeting here? 3. See, 1, 2 and 3. I said node or a junction is a point where more than two conductors meet. Even this B is also a node. I think you got it. Yeah. So that is a one technical word. Similarly, mesh or a loop. So to convince what is mesh or a loop, I will name some extra point in the diagram just for our convenience. I have named this point as C, this point as D, this point as E and F, EF. Even I can name this point as G and H. Question is, what do you mean by mesh or a loop? Mesh or a loop is a closed path for a current in an electrical network. See, for example, A, D, C, B, F, E, EA. A, D, C, B, F, E, A is a mesh. It is a closed path for a current. Or I can give one more example in the same circuit diagram. A, D, C, B, G, H, E, A, D, C, B, G, H, A. it is also a mesh or a loop. Or even I can think of giving one more example. See this. B, F, E, A, H, G, B. B, F, E, A, H, G, B. Even that is also a mesh. Mesh or a loop is a closed path for a current in an electrical network. So look at those three examples which I have highlighted. AD, CB, FEA. Or I gave one more example of AD, CB, GHA or B, F, E, A, G, H, B, right? What you notice here is, when you are naming the mesh, from which point you start, at the same point you should end. Then only it will become a closed path. Suppose if I say that A, D, C, B, F, E, is it a mesh? A, D, C, B, F, E, is it a mesh? Obviously not, because it is not a closed path. I started from A, ending at E, it has become an open circuit. I have not considered E to A path. So that is the one thing you should notice. When you name a mesh, from which point you are going to start naming, at the same point it has to end. Then only it is called as a closed path. And one more thing you can highlight in those examples. When you name the mesh, you can name the mesh either in a clockwise direction or in a anti-clockwise direction. That is left to you. See, you can make out in the first example, A, D, C, B, F, E, A. I have named a mesh in a clockwise direction. Then in the next example, A, D, C, B, G, H, A. I have named a mesh in a clockwise direction. In the next example, B, F, E, A, H, G, B. I named a mesh in a anti-clockwise direction. You can name the mesh in a two optional direction, either in a clockwise or in a anti-clockwise. But keep in mind that from which point you start naming the mesh, at the same point it has to be ended. Then only it will become a closed path. And why I am stressing the word, you can name the mesh in a clockwise direction or in a anti-clockwise direction, you will come to know soon. Because the direction in which you name a mesh, clockwise or anti-clockwise, it takes a very important role when we use a sign convention, when we study these laws called Kirchhoff's laws. So for a time being, before I take up Kirchhoff's laws, you should know the meaning of these two technical words. That's all. One is a node or a junction. It is a point where more than two conductors meet. One more is a mesh or a loop. It is a closed path for a current in an electrical network. I think it is clear to you. Okay, let us proceed further. So when I said Kirchhoff's laws, it is understood that there is more than one law. That's why it is laws, more than one law. So there are two laws actually. One is named as, of course, like your Newton's laws of motion, there is a first law, second law, third law. The first one in the order you can call it as Kirchhoff's first law, Kirchhoff's first law, which is also called as Kirchhoff's current law. In a short form, we call it as a KCL. What do you mean by KCL? Kirchhoff's current law. Other one, Kirchhoff's second law, which is also called as Kirchhoff's voltage law. Very easy to remember. First one is a current law, second one is a voltage law. So we'll take up the second law later. Let us wind up with the first law. Kirchhoff's first law or Kirchhoff's current law. You know that in physics, laws are purely based on the practically observed true facts. It is not because the scientist has said like this, things are happening. Things are happening like that. Things are observed like that. The observation made by the scientist, the practical observation made by the scientist, they have presented that observation in the form of a simpler format. We consider them as rules or laws in physics. This is also one among them. When you say a law, there will be a statement which makes the things very easier to understand. That is the importance of all the laws in physics. Kirchhoff's first law, which is also called as a current law, states that algebraic sum of the current at at a node is equal to 0. Kirchhoff's first law or current law states that algebraic sum of the current at a node is equal to 0. Now the next question is how to apply this law in a given network. So it is a very important one we're supposed to understand. And when I explain how to apply this law in an electrical network, at the end you will come across one more alternative statement for a Kirchhoff's current law or first law. So keep in mind whatever the statement I said. So assume that I'm having a big electrical network. I'm not dealing with the entire electrical network, I'll be dealing with a part of the electrical network. In the part of the electrical network, let us say I'm dealing with one of the node in the electrical network. Here you can see conductors having a resistance, right? And let us assume that in this particular part of the circuit, technically you can call it as a branch, you are familiar about that word. Current is I1, whatever the arrow mark we indicate, it is a conventional current. Current is I1. Let us say in this branch current is I2. Let us say in this branch current is I3. Let us say in this branch current is I4. Let us say in this branch current is I5. Don't be fooled by the diagram. I already told you I'm having a big electrical network and I'm dealing with a part of the electrical network. See, these ends of this resistors are not simply hanging over there. They are connected to some other part of the circuit. Then only I can expect a current I1, I2, I3, I4, I5. Correct? Okay. So this particular point, technically we call it as a node. That is what I started the topic today. Node or a junction is a point in an electrical network where more than two conductors meet. I will name that node as A. How many conductors are meeting according to the circuit diagram? Obviously 5 conductors. Let us apply KCL to a node, because you know KCL is applied to a node. Kirchhoff's current law states that algebraic sum of the current at a node is equal to 0. But when you apply KCL, there is one sign convention we follow. You know that sign convention for our convenience. For example, last year motion in a straight line, you have used a Cartesian sign convention. And this year in ray optics also we use a sign convention for our convenience. Similarly, here also we follow sign convention in applying this law. The sign convention what we follow is, and what you are going to follow will be, current entering the node we are going to take it as positive, and current leaving the node we are going to take it as negative. I said current entering the node will take it as positive, current leaving the node we are going to take it as negative. Okay, I will apply Kirchhoff's first law. Kirchhoff's first law states that algebraic sum of the current at a node is equal to 0, correct? Okay, let us start with this, I1. I have to add all the currents according to this, but following a sign convention. What do you think? I1 is plus I1 or minus I1? Plus I1, because current is entering the node. Plus of, algebraic sum, no? Plus of I2. Plus I2 or minus I2? Obviously plus I2, because current is entering the node. Plus of, what about I3? Minus I3, because current is leaving the node. So plus of minus I3 is obviously minus I3. Next one, I4, plus I4 or minus I4? Minus I4, because current is leaving the node. I5, minus I5, because current is leaving the node. I hope you understood. That should be equal to algebraic sum of the current at a node is equal to what? 0. This is how you have to apply Kirchhoff's first law. Don't you think by rearranging, I can rewrite the above equation as I1 plus I2 is equal to I3 plus I4 plus I5? What is I1 plus I2? Use a little bit of a common sense. It is nothing but sum of the currents entering the node. What is I3 plus I4 plus I5? It is sum of the currents leaving the node. So I said in the beginning, at the end of this discussion, you will come to know the alternative statement for a Kirchhoff's first law. Instead of presenting the Kirchhoff's first law as algebraic sum of the current at a node is equal to 0, you can also give the Kirchhoff's first law as sum of the current entering the node is equal to sum of the current leaving the node. Sum of the current entering the node is equal to sum of the current leaving the node. This is an alternative statement. And you will be more comfortable using KCL, especially when you are tackling the problems, rather than this particular statement. You will be more comfortable with this statement. Within no time you can apply KCL if you have this idea. Sum of the current entering the node is equal to sum of the current leaving the node. What do you mean by current? Flow of charges. When they say sum of the current entering the node is nothing but amount of charges entering the node in some time is equal to sum of the current leaving the node, means same amount of charges are leaving the node in the same time. Whatever the charges enter the node in some time, same number of charges are leaving the node at the same time, means no charges are accumulated at the node. That is why we say that Kirchhoff's first law signifies the law of conservation of charges. The amount of charges entering the node in a given time is equal to the amount of charges leaving the node in the same time, indicating that no charges are accumulated at the node, which means I can conclude that Kirchhoff's first law signifies the law of conservation of charges. So this can be a possible 1 mark question. What is the significance of Kirchhoff's first law? It signifies law of conservation of charges. I hope you follow. So one simple problem I'll discuss here only related to Kirchhoff's current law. You don't bother about the entire circuit, you just look at the circuit which will be given to you. If I say that here there is a current of 2 ampere entering, here there is a current of 3 ampere entering, and here there is a current of 4 ampere leaving. And here they said current of 1 ampere is there. What is the current here? What is the current there? So here, if you apply KCL to this particular node, current is entering 2 ampere. Here current is entering 3 ampere. Here current is leaving 4 ampere. What is the current here? That is their question. So of course it is understood that out of 2 ampere, 1 ampere flows here. Remaining 1 ampere should flow here, no? Correct? So out of 2 ampere, if 1 ampere flows here, remaining 1 ampere should flow here. Now this 1 and 3 will add up together and they flow here, 4 ampere. Correct? I am applying KCL. So I'll repeat again whatever I said. See, this was a given problem. Don't bother about entire circuit, I said. Problem is given like this. There is a 2 ampere entering, there is a 3 ampere entering, and here there is a 1 ampere, and here there is no current mentioned, and here the question is what is I? So here what I can say here is, out of 2 ampere there is no other branches. Out of 2 ampere, if 1 ampere flows here, remaining 1 ampere should flow here, correct? Isn't it? Now apply KCL. Sum of the current entering the node is equal to sum of the current leaving the node. 2 ampere is entering and 2 ampere is leaving. What is the current entering the node? 2 ampere. What is the current leaving the node? 1 ampere and 1 ampere. Now this 1 ampere and 3 ampere is entering. Together they should flow as a 4 ampere here, right? Isn't it? Now this 1 ampere is entering, 4 ampere is entering here. What should be the current here? 3 ampere. Out of 4 ampere, 3 ampere flows here, means what should be this I? Obviously 1 ampere. That is answer. Direct way of answering it. 2 ampere is entering, 1 ampere is already given as the current flowing to this point. Out of 2 ampere, 1 ampere flows here, means remaining 1 ampere should flow here. And that 1 ampere and 3 ampere will add up here. Together they flow as a 4 ampere. And out of 4 ampere, 3 ampere should flow here. Then only the current here expected to be 4 ampere. then the remaining current here, out of 4, 3 flows here means the remaining should be 1 ampere. So this idea you should develop quickly. Now I have solved using KCL, but I have not explained in detail. See, for your reference, I don't mind explaining in detail, because in the beginning you may find it difficult to understand that direct explanation given, but I said I have solved using KCL. Here there was a 2 ampere current, and here there was a 3 ampere current was mentioned in the problem, and here there is a 4 ampere current was mentioned, and here there is a 1 ampere, it was mentioned, and you are asked to find out what is I here. That's all. So what I did is I applied KCL. I'll start with this node A. According to diagram, 2 ampere is entering, 1 ampere leaving means KCL is not valid. Sum of the current entering the node should be equal to sum of the current leaving the node. Out of 2 ampere, 1 ampere is leaving this side means no other option. 1 ampere should flow in this part. So I can redraw it. Problem is already there on the board. This is 2 ampere, this is A, this is 3 ampere, this is 4 ampere given already, and here they mentioned 1 ampere. Question is, what is I? I said when you use KCL, 2 ampere is entering, 1 ampere is leaving means KCL is not valid. 2 ampere entering means 2 ampere should leave. Out of 2, 1 flows here means remaining 1 ampere should be here. Can I say B is also node? 3 ampere is entering, 1 ampere is also entering the node. What is the total current entering the node? 4 ampere. That means 4 ampere only should leave the node. No. Correct? Next. Let us name this as a node C. 4 ampere is entering, I ampere is leaving. 4 ampere is entering, I ampere is leaving. Now I am not unable to solve it directly because I don't know. If I name this as a node D, I don't know what is the current in CD. So we'll go back to this. 1 ampere is entering, 4 ampere is leaving means there is no meaning. Sum of the current entering the node should be equal to sum of the current leaving the node. What is the current leaving? 4 ampere. What is the current entering? 1 ampere. That means in this branch there should be a 3 ampere directed like this. That means 3 ampere and 1 ampere should enter and 4 ampere should leave. Now you can answer this. 4 ampere is entering the node C. Out of 4, 3 ampere is leaving the node C means what is the remaining current? Obviously 1 ampere should leave the node. I hope you follow. So this is one simple question I have discussed in finding out the current and the application of the KCL. Is it clear? So make these things clear. Kirchhoff's current law or Kirchhoff's first law states that algebraic sum of the current at a node is equal to 0, or alternative that sum of the current entering the node is equal to sum of the current leaving the node. And the point to be noted is sign convention which I followed. Current entering the node is taken as positive, current leaving the node is taken as negative. At the end I concluded that it is better to apply KCL by remembering this statement rather than this. Followed? We'll move on to the next one, Kirchhoff's voltage law. Kirchhoff's second law, which is also called as a voltage law. In a short form we call it as a KVL. So this is actually a very important one, and further concepts and most of the problems in this topic require a help of this law, Kirchhoff's second law or Kirchhoff's voltage law. First let me tell you the statement of the law, what actually this law says. Then after that we'll learn how to apply the law. Kirchhoff's second law or Kirchhoff's voltage law states that algebraic sum of the change in potential around the loop across the resistors and the cells is equal to 0. I'll repeat the statement, listen. Kirchhoff's second law or Kirchhoff's voltage law states that algebraic sum of the change in potential across the loop or around the loop across the resistors and the cells in a mesh is equal to 0. In a simple word, you can write the entire statement as algebraic sum of V is equal to 0 in a mesh. KCL is applied to a node. KVL is applied to a mesh or a loop. This particular statement which I said, Kirchhoff's second law or Kirchhoff's voltage law states that algebraic sum of the change in potential around the loop across the resistor and the cells is equal to 0 can be also given as algebraic sum of the product of the current and the resistance in a mesh or a loop is equal to algebraic sum of the EMFs. This is an alternative one. In a mesh or a loop, algebraic sum of the product of the current and the resistance is equal to algebraic sum of the EMFs in the mesh. Even that statement is also true, correct statement. Actually, it gives the same meaning. But when I explain you how to apply KVL to a mesh or a loop, I'll give a sign conventions which are valid for this particular statement. Suppose if you go for this particular statement and if you are trying to apply Kirchhoff's voltage law to the mesh or a loop using this idea, there is a small change in the sign convention which you are supposed to follow. So make it clear. If you are following this particular statement and that particular equation, sign convention which we have to use in applying KVL to a mesh is slightly different. There is a difference. So I'll stick on to this particular relation and I will explain you the sign convention related to this. Kirchhoff's second law or Kirchhoff's voltage law states that algebraic sum of the change in the potential around the circuit across the resistors and the cells is equal to 0. What do you mean by summation of IR? It is V only, correct? Even this EMF is also something related to the potential difference only. Ultimately, it ends up with this relation. Now let us learn how to apply Kirchhoff's second law or KVL, especially the sign convention. That is very important. Assume that you have been given one electrical network. You don't bother about the network. It is already given to you. This is electrical network. The network which was given to you has got cells, has got resistors. You can notice. For your reference, I will name this resistor as R1 and this cell is having a EMF E1. Let us say its internal resistance is small r1 and this cell has got a EMF E2. Let us say its internal resistance is small r2 and here there is a resistor of resistance R2 and here there is a resistor of resistance R3 and these corners has been named for our convenience. Let us say A, B, C, D. This corner let it be E and this corner let it be F. I said I am explaining you how to apply Kirchhoff's voltage law and sign convention which you are supposed to follow. When circuit is given to you like this, first of all you should identify how many branches are there in the circuit. Best logic, how to find out how many branches are there, you stand at the node, you position yourself at the node. Can I call B as one of the node? Of course we know even A is also one of the node only. If you stand at B, don't you think that here there is one path, here there is one path, here there is one path to reach A? Means how many branches are there? Surely 3. Means if I start from this node, I can reach this node A in the path B, C, D, A. One option. Second option, B, E, F, A. Third option, B, 2, A. 3 options I have, which gives a clear indication that there are 3 branches. When you have 3 branches, I can expect a 3 different current. Assume that in the first branch, let the current be I1. So this is the first thing you're supposed to do when the circuit is given like that. Before you apply KVL, when the current was not marked in the circuit, first of all you have to identify how many branches are there. Then you have to indicate the current in the branches. Let us say current in this branch is I1, current in this branch let it be I2, current in the third branch let it be I3. I1, I2 and I3 are the current in the various branches. Now the question is, what is the direction of the current? Right? The first rule is, after knowing how many branches are there and how many different currents are there, when the question arises, what is the direction of the current? The direction of the current is selected arbitrarily. I said direction of a current is selected arbitrarily. Direction of the current is selected arbitrarily. What do you mean by that? Coming to this I1, what is the possible directions of I1? It is from B to C, C to D, D to A, or it is from A to D, D to C, C to B. Direction of I1, I said it can be from B to C, C to D, D to A, or from A to D, D to C, C to B. 2 options are there for that current. I am talking about conventional current. Which direction? You can select direction arbitrarily. It is your choice. It can be from B to C, C to D, D to A, or from A to D, D to C, C to B. Any one direction you select. Let me select the direction of a current in this manner. B to C, which means it is directed from C to D, D to A. It is my convenience. I selected in that direction. Means the direction of a current can be selected arbitrarily. But once you select the direction of a current from B to C, here you don't reverse the direction of a current. It can't be from D to C. It should be in one direction. This is still, we are talking about DC. I mean, even if it is AC also, at a time current cannot be in both the directions there. Okay. So here current is selected in one direction, I1. Next question may be there in your mind. If the direction of the current in the branch is not as we have selected, if it is opposite to that, you need not break your head. If it is opposite to that, when you do some calculation, suppose if it is in the problem, you will get the answer for I1 as minus. I1 is supposed to be a 2 ampere, you will get the answer as minus 2 ampere. Minus answer in the current indicates that direction of a current is not as you indicated, it is opposite to it. You need not go to change the direction, let it be. When you are including that current in any of the equation, include the current with the negative sign. I think it is clear to you. I'll repeat. Now the question arises, if the direction of a current in the branch is not as we selected, it is opposite to that. I said you need not break your head. When you do the calculation in the problems, you will get the answer with the negative sign. Negative sign for the current indicating that direction of a current in the branch is opposite to what you have indicated. You need not change the direction. Clear? Okay. So I1 I marked. Let us give an arbitrary direction for I2. Let us say I2 is in this direction. B to E, E to F, F to A. You had other option also. It could have been from A to F, F to E, E to B, right? Any one direction is selected. That is the first rule. Direction of a current is selected arbitrarily. And here I3 will select it from A to B. Your convenience, you can change the direction. It can be taken from B to A also. Clear? Okay. So I1, I2 and I3 directions are selected arbitrarily. And one more suggestion I would like to give you. Suppose in a branch, if there is a cell, in a branch if you find there is a cell, try to assign a direction of a current as sent by the cell. Do you have a cell in this branch? Yes. This is the positive of the cell, right? This is the negative of the cell. Cell always sends a current from positive to negative, conventional current. See? Here, do you have a cell in this branch? Yeah, positive, negative. Cell always try to send a current from positive to negative. Of course, you need not follow the suggestion that is left to you, because the direction of a current can be selected arbitrarily. But I said, if you have a cell in the branch, try to select the direction of a current as sent by the cell, convenient for you. In the third branch, I don't have a cell, you select one particular direction. But it's just a suggestion, you need not follow that. You can just stick on to the rule. Direction of a current is selected arbitrarily. You have only two options, one of the option you select. Okay. Then the second step. You have to select one mesh. You have to select one mesh. After that, I will explain the sign convention. I will select a mesh where I am going to apply KVL. You know that Kirchhoff's voltage law is applied to a mesh. Apply KVL to a mesh. A, B, C, D, A. I am applying KVL to a mesh. A, B, C, D, A. When you apply KVL to a mesh, I said no, you have to follow some sign convention. It is supposed to be algebraic sum of V should be equal to 0. When you say algebraic sum of V, it involves product of IR, it involves EMF, everything. It involves product of IR, it involves EMF, everything. I said you should be careful where you are. I am explaining a sign convention with reference to this. We'll go according to the order in which I have named the mesh. I have named the mesh as A, B, C, D, A. Tell me, I have selected a mesh in a clockwise direction or an anti-clockwise direction? Obviously, I have selected a mesh in a anti-clockwise direction. So I will draw that direction, the anti-clockwise direction in which I selected a mesh. Technically, we call this as a direction of a traverse. What do you call it as? Direction of a traverse. Direction of a traverse means the direction in which the mesh has been selected. The direction of a traverse is a direction in which the mesh has been selected. And the direction of a traverse has got very important role in assigning a sign convention. Okay. So what I'll do is, when I deal with the algebraic sum of V, which involves product of IR as well as EMF, so let me start with the product of IR first. Move from A to B. Move from A to B. When you are moving from A to B according to direction of a traverse, do you meet any resistor on the way? Yes. Who is that? R3. What is the current through the resistor? I3. What is the product of current in the resistance? I3 into R3, which is nothing but V, correct? I3 into R3. Fine. Now the sign convention for the product of I and R, which is nothing but potential drop, change in potential across R3, correct? Yeah. The sign convention is, if the direction of the current in the branch, if it is same as the direction of a traverse, then the product of I and R should be taken as a negative. I'll repeat. If the direction of a current in the branch, if it is same as a direction of a traverse, then the product of I and R is taken as a negative, otherwise positive. What do you mean by otherwise positive? If the direction of a current in the branch is opposite to a direction of a traverse, then the product of I and R should be taken as positive. For example here, what is the direction of a traverse? A to B. I have to take a mesh A, B, C, D, A, no. I selected a mesh in that direction. A to B is the direction of a traverse. What is the direction of a current in that? A to B only, I3. I3 is directed from A to B, correct? What is the product of current in the resistance? Obviously, I3 into R3. Plus or minus? Minus. Why? Because direction of a current in the branch is same as the direction of a traverse. Product of IR should be taken as negative. Fine. I reached B. Now I have to proceed further. B to C. You don't have a resistance because these are the connecting wires. Connecting wires are copper wires. They have a negligible resistance. Product of IR can be ignored. So I reached C. Now move from C to D. Always you go in this order. There won't be any confusion. Now I'm moving from C to D. When you move from C to D, who is the first resistor you meet on the way? R1. What is the current through it? I1. This is I1, no? Here I1, even here also I1 only. It is the same current, because as long as the branch is same, current should be same. This is I1. So what is the product of current in the resistance? I1 into R1. I1 into R1 plus I1 into R1 or minus I1 into R1. Obviously it is minus, because the direction of a traverse is from C to D. Direction of a current is also from C to D. So product will be negative. If the direction of the current in the branch is same as the direction of a traverse, means product of IR is taken as negative. Okay. Do you meet any other resistor when you are moving from C to D after capital R1? Yes, there is an internal resistance for the cell, small r1. What is the current through it? I1 only. What is the product of current in the resistance? I1 into small r1. Plus I1 into small r1 or minus I1 into small r1? Again minus, because direction of a traverse is from C to D and direction of the conventional current is also from C to D. So product should be taken as a negative. Correct? Where we reached? We are at D. Proceed. Move from D to A. Move from D to A. If you move from D to A, do you meet any resistance? Yeah, it is a negligible resistance. Connecting wire. Product of IR can be ignored. Right? So one around the circuit is over, where we come across product of IR. That part is over. Don't you think there is a potential drop across the cell also? Right? There is a EMF also. Isn't it? There is a EMF. So this EMF, E1, I would include in this, because that also comes as algebraic sum of V across the resistor and across the cells in the given mesh or a loop should be equal to 0. So product of IR is over. Now you start from A again. A to B, do you have A to B? Why I am taking from A to B? Because the mesh which was selected is from A, B, C, D, A. A to B, do you find any cell or any EMF? No. B to C, any EMF? No. C to D, do you find any EMF? Yes. What is EMF of the cell? E1. E1. Now the sign convention for the EMF. Of course, when I say sign convention, it should be either plus E1 or minus E1. See, when it is plus E1 and when it is minus E1. When you are moving along the direction of a traverse, A to B, no cell, B to C, no cell, C to D, there is a cell. I have to move in this direction, right? Along the direction of a traverse when I am moving. When you are crossing the cell, you are moving from the negative terminal to the positive terminal of the cell. That means you are moving from a lower to a higher potential, means potential is increasing. That time EMF will be taken as plus EMF. Plus E1. When you are crossing the cell, when you are moving along the direction of a traverse, when you cross the cell, if you are moving from negative terminal to the positive terminal, means that time EMF will be taken as plus E1. Otherwise it is minus E1. What do you mean by otherwise minus EM? If the direction of the traverse is selected such a way that when you are crossing the cell, if you are crossing the cell from positive of the cell to the negative of the cell, that time EMF will be taken as minus. Now tell me, EMF should be plus E1 or minus E1? Obviously it is plus E1, because according to direction of a traverse, when I move, when I cross the cell, I am moving from negative to the positive of the battery, that time plus E1. That should be equal to 0. That is taken as equal to 0. Algebraic sum of the change in the potential around the loop across a resistor and cells is equal to 0. That is equal to 0. I hope you followed. I'll give one more example to make it more clear. I will apply KVL to a mesh ADCBA. I am going to apply KVL to a mesh ADCBA. See, what you notice here is, in both the examples, in the first example, in the second example, I am dealing with the same mesh. Can you notice that point? Earlier I applied KVL to a mesh ABCDA. Now I am applying a KVL to a mesh ADCBA. Mesh is same, but the direction of a traverse is opposite. ADCBA. Now for a time being, I'll change this direction of a traverse because I have to apply KVL to that mesh. Now I selected a mesh in which direction? Yeah, clockwise direction. Earlier I selected in anti-clockwise direction. Now I selected a mesh in a clockwise direction. See, this is the direction of a traverse. That is very important. It takes a very important role in giving a sign convention for product of IR and EMF. I told you already. Okay. Now see. We'll go according to the order. A to D, when you move, do you find any resistance? Obviously no. Of course, even though there is a resistance also negligible, connecting wires have a negligible resistance. Product of IR is 0. Move from D to C. See, be involved. Move from D to C. Who is the first resistor you come across? Small r1. Small r1. What is the current through it? I1. What is the product of current in the resistance? I1 into small r1. Plus I1 into small r1 or minus I1 into small r1? Obviously it is this time plus I1 into small r1, because you are moving from D to C. I mean to say, direction of a traverse is from D to C, but conventional current is from C to D. Direction of the current is opposite to direction of a traverse, means product of IR is taken as positive. No. Yes. Proceed in the same part, D to C. Do you meet any other resistor? Obviously there is a capital R1. What is the product? What is the current through it? I1. What is the product of current in the resistance? I1 into capital R1. I1 into capital R1. Plus I1 into capital R1 or minus I1 into capital R1? Yeah, it is plus, because direction of a traverse is from D to C, but the current in the branch is from C to D. Correct? So when the direction of a current in the branch is opposite to direction of a traverse, product of IR is taken as positive. Okay, we reached C. No other resistor we found in between. C. We'll move from C to B. C to B. Do you find any resistance? No. Even though there is a resistance, negligible one, connecting wires, you can ignore. Product of IR will be 0. I reached B. Now you are left out. You have to end up with the same point where you started. I have to move from B to A. Don't live in between. I have to move from B to A. What is the resistance you meet on the way? R3. What is the current? I3. What is the product of current and the resistance? I3 into R3. What do you think? Plus I3 into R3 or minus I3 into R3? It is also plus, because direction of a traverse is from B to A. Current direction in the branch was A to B. So it is plus I3 into R3. I think you followed. So algebraic sum of the potential drop across resistors are over. Now I have to left out with the cells, right? Cell. So it is always better you go in that order. First you finish the product of IR, then you'll go back to the EMF. No confusion at all. Once again you have to go back to the mesh. A to D. I have to go in the same order we have selected a mesh. A to D, do you find any cell? No. D to C, do you find any cell? Yes. What is the EMF of the cell? E1. Now I am going along the direction of a traverse. A to D. D to C means I should move like this. D to C. Now the sign convention for EMF. When you are crossing the cell, if you are moving from the positive terminal to the negative terminal of the cell, means EMF will be taken as minus E1. Minus of that EMF. If when you are going along the direction of traverse, if you are moving from negative to positive, means potential is increasing. That time EMF is positive. Now when you are moving along a direction of a traverse, which I named D to C, positive to negative means potential is decreasing. That time EMF will be taken as minus is equal to 0. My question to you is, in the first example, in the second example, I was dealing with the same mesh. But only difference was, in the first example, I have selected a mesh in a anti-clockwise direction. In the second example, I selected a mesh in a clockwise direction. Look at the answers what you have. Do you find any change in the answer? This answer what I gave you earlier and this answer what I am having now, is there any change in the answer? Obviously not. They are one and the same. You change the sign throughout. No, mathematical allowed. What are you going to get? Minus I1 R1, minus I1 capital R1, minus I3 R3 plus E1 is equal to 0. This answer, whatever I have written here, and this answer are one and the same. What I am trying to tell you by giving this example is, doesn't matter whether you select a mesh in a clockwise direction or in a anti-clockwise direction, but you have to follow sign convention neatly, clearly, answers will be same. Whether you select a mesh in a clockwise direction or in a anti-clockwise, it doesn't matter. But you follow the sign convention systematically, properly, you will get the same result, same answer. I hope you followed. So let me wind up this with one more example. Just to make it 100% clear, like you should know how to apply KVL to a mesh. You try by yourself, apply KVL to a mesh. I will increase the speed with which I am writing the equation. I am going to apply KVL to a mesh. Let us say A, B, E, F, A. I am applying KVL to a mesh. A, B, E, F, A. Okay. First I will start with the potential drop across the resistor. Then we will take up a EMF of a cell. We will go in that order only. A to B. What is the product of IR? You try to answer by yourself so that you will get involved in the subject. A to B. What is the product of IR? I3 into R3. What do you think? Plus I3 into R3 or minus I3 into R3? Obviously it is minus I3 into R3 because direction of a traverse is from A to B. Direction of a current is also along the direction of traverse. Product of IR is taken as negative. So it is minus I3 into R3. Followed? Okay. So B to E, do you find any product of IR? No. B to E product of IR is 0. Move from E to F. When you move from E to F, who is a resistor you come across first? Capital R2. What is the current through it? I2. What is the product of current and the resistance? Minus I2 R2. I am telling the answer with the sign convention. Why minus I2 R2? You think, no. What is the direction of a traverse according to the naming? E to F. What is the direction of a current? E to F. What is the product of IR? Obviously negative only because direction of a current is same as direction of a traverse. That time product of IR is negative. I2 into R2. Do you find any other resistor in the same branch? Yes, small r2, internal resistance. What is the current through? I2 only. As long as branch is same, you must be knowing current is same. As long as it is a single branch, throughout current is same. So what is the product of IR? I2 into small r2. Can I write minus I2 into small r2? I think you are getting a better idea. Okay, so I reached F. Move from F to A. Product of IR is 0. Right? Okay, algebraic sum of product of IR is over. Now let us refer the EMF. How many A to B do you find any EMF? No. Any cell? No. B to E, no cell. E to F. You are moving from where to where? E to F. When you are moving from E to F, means you are moving from negative terminal to the exactly positive terminal of the battery, means potential is increasing. That time EMF should be taken as positive. So it should be plus E2, that is equal to 0. This sign convention you follow. Don't have any confusion. Remember the sign convention what I explained. Writing everything, my product of IR and EMF at the same side. Product of IR and EMF at the same side. That is the sign convention you follow. Just for your knowledge I can tell you. Suppose if you are going for this particular statement, algebraic sum of IR is equal to algebraic sum of EMF. Just for your knowledge, you have to reverse the sign convention which I gave for EMF. Summation of IR it is same method. Mesh you have to select one particular direction of a mesh, you have to select all direction of a traverse, either clockwise or anti-clockwise. First you have to see product of IR. When you go for a product of IR, same sign convention what I explained to you. Understood? That is at left side. Then if you write algebraic sum of EMF at the other side, if you write algebraic sum of EMF at the other side, you have to reverse the sign convention for EMF which I said. You know what do you mean by reversing? If you are writing EMF other side, when you are crossing the cell, if you are moving from negative to positive, that time EMF will be taken as minus E. If you are writing at the other side of the equality. Don't you think that if I shift this E to the other side, it will become minus E2? That's all. You have to reverse the sign convention which I gave for EMF. If you are following this equation. So don't give much concentration for that. Whatever I explained the sign convention, you follow that. Just for your knowledge I mentioned. If you are writing the algebraic sum of EMF at the other side, you have to reverse the sign convention which I gave for a EMF of a cell. Remaining things are same. I hope you followed. So this is how we apply Kirchhoff's second law or voltage law to the mesh. So don't forget the sign convention. So now we have reached a stage where I can give an example, one more simple example from your earlier knowledge. See, when you have studied about a cell, I mean to say sources of EMF, you have come across a simple circuit. For a simple circuit, you have applied Ohm's law. There is a cell of EMF E, internal EMF E, comma, internal resistance R, and there is a external resistance capital R. If I ask you to apply KVL, to a mesh, I need not name the mesh because only one mesh is there. I need not name the mesh because in the earlier problem which I explained, there were two different mesh. I need to name the mesh. But here I need not name the mesh, but I have to select the direction of a traverse for the mesh, which I have a two optional direction, either clockwise or anti-clockwise. Shall I select in this particular direction? What do you call it as? A direction of a traverse. So we know that already, since there is only one cell connected to this resistor R, can I say that here I can expect a current I? I can expect a current I throughout the circuit. Current direction, conventional direction, normally we name it from positive to negative. No, anyhow there is no confusion here because there is only one cell. Let us say current is I. Now I am applying KVL to a mesh. I am going in the opposite order, remember. I have selected a mesh, direction of a traverse. Mesh is only one. Select a direction of a traverse in an anti-clockwise direction, which is opposite to a conventional current in the circuit. Please remember that. Shall I move from here? What is the product of IR? Current is I. Current is I, resistance is R, correct? What do you think, plus IR or minus IR according to KVL? Direction of a current is same as the direction of a traverse, right? I select a direction of a traverse in anti-clockwise direction. Current is also in anti-clockwise direction in the mesh. So it should be minus IR. So I moved from here to here, product of IR is minus IR. I'm moving from here to here. What is the product of IR? 0. I'm moving from here to here. Do you meet any resistance? Yes, small r. What is the product of IR? I into small r. Current is same, no, single branch, current is same. Plus IR or minus IR? Minus. Because direction of a current is same as the direction of a traverse. Product of IR will be negative. Direction of a current in the branch, if it is same as the direction of a traverse, product of IR is negative. So I said direction of a current and direction of a traverse are same, not opposite. Make it clear, make it. Direction of a current and direction of a traverse are in the same direction. So product of IR is negative. Product of IR is negative. You move from here to here. No resistance. I'll repeat. I started from here to here. Product of IR is minus IR. You understood why it is minus IR. Direction of the current in the branch and direction of a traverse are same. Here there is no product of IR. Here to here the product of IR is I into small r. Minus. Here to here no product of IR. Okay, product of IR is over. Next EMF. If I move along the direction of a traverse, negative to positive, EMF is increasing or decreasing? Increasing. So negative to positive. So I should take that EMF as plus E. Should be equal to 0. Rewrite. This E will be equal to, can I take this to the other side? What do you get? I into capital R plus I into small r. Don't you think the same equation you had in the simple circuit consisting of a single cell and external resistance? Same formula you had. And using this only you got expression for current. You took I common, you are left out with capital R plus small r, or I is equal to E by capital R plus small r. This is expression for a current. See, I got it using KVL. I hope you followed this. See, one more problem I will take up here with the help of KVL, which you can solve. So it is a problem asked in one of the competitive level exam. problem is given like this. So already problem is given to you. I mean to say the circuit is there in the problem. You are asked to find potential difference between A and B. The question is, you are asked to find out potential difference between A and B. Everything is mentioned in the problem. Everything is mentioned in the problem. You can make out here there is a 6 ohm resistor, here there is a 9 ohm resistor, here there is a 5 ohm resistor, and here I am having a cell of EMF 12 volt, here I am having a cell of EMF 4 volt, everything is given. Even current is also mentioned. Current is given as 2 ampere and direction of the current is also given. And now the question arises in your mind, how this problem can be correct because circuit is open. No, circuit is closed. We are not bothered about the entire circuit. It is a part of the circuit. It is a part of the circuit where you are asked to find out the potential difference between A and B. You are just asked to find out the potential difference between A and B. Now the question is how to solve the problem. I said problem can be solved using KVL, Kirchhoff's voltage law. But again the problem is, you know that KVL is applied to a mesh or a loop. Mesh or a loop is a closed path for a current in network. Where is a closed path? We will close the path, no? What is there? If that question is in your mind, if you are solving the problem using KVL, KVL is applied for the closed path. Where is the closed path? We will close the path. Now how to start the problem? This is a question given to you. What you need to know is, I'll redraw the circuit for your reference. Same circuit I am redrawing it, so that you should not have a confusion with the problem, what is actually a question asked and what happened later. I said the problem can be solved using Kirchhoff's voltage law. Within no time you can answer actually, but in the beginning, initial stage, you should understand how to apply. That's why that will take a time. First question in your mind is, KVL is applied to a closed path. I said we'll close the path. What you need to do is, you have to connect one imaginary battery between A and B. You have to connect one imaginary battery between A and B. This battery is having a EMF, let us say its EMF is V suffix AB, having a negligible internal resistance. I said you have to connect a battery between A and B, across which 2 points you are asked to find out the potential difference, and that battery which you connect across A and B will have a negligible internal resistance. When the internal resistance is negligible, don't you think that EMF itself is called terminal potential difference? Yes, that is the question, ultimate question. This is a battery having a EMF which is given as V suffix AB, but negligible internal resistance. When the internal resistance is negligible, that EMF itself is called potential difference. This VA suffix VB is understood as VA minus VB. Next question also may be there in your mind. Okay, you said connect imaginary battery across A and B, and the battery is having a EMF but negligible internal resistance. This is a EMF having a negligible internal resistance, means EMF itself is a potential difference. Fine. But which end should be connected to the positive of the battery and which end should be connected to negative of the battery? Very simple. You already know that current in that problem is directed from A to B, means A should be at higher potential. No, B should be at lower potential, because conventional current is always from higher potential to lower potential. So since conventional current of 2 ampere is directed from A to B, here it is 2 ampere, means throughout it is 2 ampere only, because in between there is no sub branches, right? So that means A should be at higher potential, B should be at lower potential, which means I should connect A to the positive terminal of this imaginary battery, B to the negative terminal of the imaginary battery. That is the meaning. If that question arises, which end should be connected to the positive, negative, you can think like that. Since current is directed from A to B, A should be at higher potential, B should be at lower potential. So A is connected to the positive terminal of the imaginary battery, B is connected to the negative terminal of the imaginary battery. Over. Apply KVL to the mesh. You're already having a closed path, right? What is the problem in applying a KVL? If you want to name the mesh, I can, for your convenience. Actually, not required, but to make it more clear, apply KVL to a mesh. Can I say A, B, C, D, A? A, B, C, D, A? Yeah. Single part, no? Current should be in this direction. Do you agree with me? Same 2 ampere. Okay, we'll move from A to B. A to B. What is the product of IR? 6 into 2. 6 into 2. What do you think? Plus 6 into 2 or minus 6 into 2? Minus. Because this was the direction of a traverse. A, B, C, D, A. 6 into 2. Minus 6 into 2. Forget about cell. We'll come back to the cell later, okay? Here also, current is in the same direction, 2 ampere, right? What is the product of current and the resistance? 9 into 2. Product is positive or negative? Again minus, because direction of a current and direction of a traverse are same. Then what is the current here? 2 ampere. What is the product of current and resistance? 5 into 2. Plus or minus? Minus, because direction of a current and direction of traverse are same. Do you have any resistance here? Any resistance here? Any resistance here? No. Product of IR will be 0. A to B, B to C, C to D, D to A is over. Product of IR is over. Correct? Now let us come back to the EMFs. See here. I am moving from A to B. When you are moving from A to B, who is the first cell you come across? This one. What is the EMF? 12 volt. Now I am moving from positive to negative. Correct? When I move along the direction of a traverse, I am moving from positive to across the cell. Positive to negative means EMF should be taken as minus. Minus 12. I hope you followed. Minus 12 volt. Okay, next. Negative to positive. I am moving along the direction of traverse. When I am moving from negative to positive, it is plus 4 or minus 4? Plus 4. Negative to positive means potential is increasing. So plus 4. Proceed, proceed. No cell here, no cell here. I am moving along the direction of a traverse. Here, negative to positive. When I am moving across the cell, it is from negative to positive. Correct? So it is plus VAB. Plus VAB is equal to what? 0. I'll write here. Plus continuation, plus VAB is equal to what? 0. I hope you are able to follow. Okay, now we'll do the simplification. Remember, V suffix AB means VA minus VB. V suffix BA means VB minus VA. That is the way you're supposed to understand. VA is at higher potential, VB is at lower potential, like that. VA is a potential at A, VB is a potential at B. VA minus VB is a potential difference between A and B. 6 into 2 minus 12, 9 into 2 minus 18, 5 into 2 minus 10, minus 12, plus 4, plus VAB is equal to 0, correct? So this is, I can say minus 18, minus 12 is obviously minus 30, minus 30, minus 10 is minus 40, minus 40, minus 12 is minus 52, minus 52 plus 4 is minus 48. Minus 48 plus VAB is equal to 0. I want V suffix AB. No. What is V suffix AB I got? 48 volt. Take it to the other side. It is 48 volt. That means answer for this problem is V suffix AB is 48 volt. When I say V suffix AB, you should understand VA minus VB is 48. If VA minus VB is 48, if they ask you a question, what is VB minus VA? Minus 48. VA minus VB is 48 means VB minus VA should be minus 48. If they ask a question, what is VB minus VA in this problem? It will be minus 48. I think you followed this. So this is one problem where you find application of KVL. I hope you followed this. Okay, so till now we have learned Kirchhoff's first law, Kirchhoff's second law, and application of the first law and application of a second law. And I told you that Kirchhoff's first law signifies law of conservation of a charge. I explained this. Similarly, Kirchhoff's second law signifies law of conservation of energy. Because you know, that time I said no. Kirchhoff's second law can be also given as the algebraic sum of the product of current and the resistance is equal to algebraic sum of the EMFs. this particular equation says that whatever the energy was utilized by the battery will be doing it is used to do some work done in moving a charge across external resistance and work done in moving a charge through the internal resistance. So based on this or based on this particular relation, I can conclude that KVL, Kirchhoff's voltage law, signifies a law of conservation of energy. So this can be a possible one more question. What is the significance of a KVL? It signifies law of conservation of energy. What is the significance of KCL? It signifies the law of conservation of charges. Now whatever I explained is the basic fundamental things, especially in this KVL is very important, and using KCL and KVL we are going to proceed further in the topic. I think you understood up till here clearly.